Hello! In this video, we are going to prove the following theorem. Suppose f is a function from a to b and g is a function from b to c. Then, g compose f is a function from a to c, and for every element a in a, we have that g compose f of a is equal to g of f of a. Now, before we begin this proof, let's first get some context. First of all, we know that functions are relations. So really, we have that f is a relation from a to b, and g is a relation from b to c. Now, g compose f is also a relation. If we recall from compositions of relations, if we have that f is a relation from a to b, and g is a relation from b to c, we can think of b as our intermediate set. And so really, we have that g compose f is a relation from a to c. But in this theorem, we actually want to prove that if f and g are both functions, then g compose f is also a function. So, we're first going to prove that g compose f is a function from a to c. What does this mean? Well, all it means is that for every element a in a, there is a unique element c in c, such that a comma c is an element of g compose f. So to prove that g compose f is a function from a to c, this is what we want to prove. And we're trying to prove a statement about every element in a, so give me an arbitrary element of a. I'll call it a. Now, because a is an element of a, and f is a function from a to b, this means f has a functional value at a. And so we could say, for instance, let b equal f of a. Now, the functional values of f are elements of b. So really we have that f of a is an element of b. So really, b is an element of b. But since g is a function from b to c, this means g has a functional value at b. So we could say, for instance, let c equal g of b. Now, the functional values of g are elements of c. So we have that g of b is an element of c. Okay, but we know that this is equivalent to saying that a comma b is an element of f. And this is equivalent to saying that b comma c is an element of g. But now, from compositions of relations, if you recall, we can think of b as our intermediate element. And we have that a comma c is an element of g compose f. So now we have found an element c in c, such that a comma c is an element of g compose f. So that proves existence. But now we want to prove that the element c that we found is unique. That is, we want to prove that c is the only element of c that satisfies this condition. So to prove uniqueness, what we can do is we can show that every element of c that has this condition is equal to c. So what we're going to do is we're going to give ourselves an arbitrary element of c. I'll call it d, such that a comma d is an element of g compose f. Our whole goal now is to deduce that c is equal to d. And to start, notice we are an element of a composition. What does that mean? Well, by definition of composition of relations, this means we can choose some element in our intermediate set B, say x, such that a comma x is an element of f, and x comma d is an element of g. So notice we have that a comma b is an element of f, and a comma x is an element of f. Because f is a function, we know that a must map to a unique element. So really, we have that b equals x. And since b equals x, this means we can take the x right here and replace it with b. So really, we have that b comma d is an element of g. And now notice we have that b comma c is an element of G and b comma d is an element of G. So because G is a function, we know that b must map to a unique element. So really we have that C equals D. And this is exactly what we wanted to prove. So we have proven uniqueness. Because what we've done here is we considered some arbitrary element in C that has the same property that C has. And we showed that D must equal C. So since D was arbitrary, that means every element in C that has the same property as C is equal to C. So C is unique, which means we have proven this statement. And since A was arbitrary, that means we've proven this statement for every element in A. So because we've proven this entire statement, that means we have proven that G compose F is a function from A to C. So now that we've proven G compose F is a function from A to C, now we're going to prove that for every element A in A, the functional value of G compose F at A is equal to this. Now, we're trying to prove a statement about every element in A. So give me an arbitrary element of A. I'll call it A. And so from here, we're actually going to perform the same steps that we performed in the existence portion, right? We can let B equal F of A, which is an element of B. And then we can let C equal G of B, which is an element of C. Well then, we know that this means A comma B is an element of F and B comma C is an element of G. And putting these two together, we know from compositions of relations that A comma C is an element of G compose F. So we performed the same exact steps that we did in the existence portion, but now that we know G compose F is a function, this means we can write that G compose F evaluated at A is equal to C. And we know that C is equal to G of B. But B is equal to F of A, so we can replace B with F of A. So now we have that G compose F of A is equal to G of F of A, which is exactly what we wanted to prove. And since A was an arbitrary element of A, this means for every element A in A, this is true. So we have proven both parts to the theorem. So this completes the proof. And yeah, this is one way in which you could prove this theorem. So yeah, that's pretty much it for this video.